Symmetric difference. So, what difference does it make in your life, this concept? You see, when we move from numbers to sets, on one hand, a lot has changed. For example, with numbers, with natural numbers at least, we had 0, 1, 2, 3. So they were organized in a nice linear way. But now when we move to sets, we've got empty set, we've got singleton of empty set. So far it seems to be fine. But then we have two different candidates for number 2, right? We have this one and this one. So the way I make a progression is that every next one is obtained by putting the previous ones into a set. But then you know that there is exponential growth here. So we have much more sets than we have numbers in a way. Yeah? So the objects have changed, the multitude has increased. But what hasn't changed is that just like we have basic relationships and operations on numbers, there's something similar going on here as well. So for numbers we have less or equal, we have plus, we have multiplication and other things, right? These are 3 basic ones, others can be defined using these. Well, even some of them can be defined using the others. For sets, we've got subset inclusion. And we have operations such as union, intersection, we have power set, and so on. Well, in one of the examples for a universe of sets without the axioms, you saw that the power set can capture the idea of adding 1. And then the union of a single set capture the idea of subtracting 1. But then we also have Cartesian product, right? And so if you think of Cartesian product being the analog of multiplication and maybe union analog of addition, then the intersection has no analog in the number world. So we have some new operations emerging in this world that we didn't have there. And one of them is also difference of sets. Well, in a way, maybe we got it there. It's subtraction of numbers. But then there is another kind of difference, which is symmetric difference. And one of the students, I think her name is Brittany, pointed out in one of the other lectures that maybe we can think of the symmetric difference as taking absolute value of the difference. So we've got this operation for numbers, assigning to x, y, the absolute value of x minus y. And so she pointed out that in some sense symmetric difference of sets is an analog of this operation. And it's a very interesting remark because this operation for numbers is a very important thing. It measures the distance between the two numbers. So maybe we can think of symmetric difference as a way of measuring distance between two sets. And in a way it measures the distance because, right, what is symmetric difference? So let's recall that. So we've got two sets, right? Now this symmetric difference is going to be this shaded area. And so it does measure how far the two sets are from each other. This far. If not for this extra bit, they would have been the same set. It's a nice idea. Okay. So what I want to explore in this lecture with you is what properties does the symmetric difference have and how we can think of these as being actually quite natural properties from our experience with numbers. So that's another ingredient I want to add here before we move on to focusing on the symmetric difference. We've got the operations and relationships, but we also have the laws the axioms, the identities, the theorems. Beautiful formulas that express fundamental principles to which these operations adhere. For example, A plus B plus C equals A plus B plus C, right? We might think, okay, this is such an easy thing, but this is so useful. It's extremely useful. Almost every day, I'm sure we use it a lot. This is what allows, this together with this one, is what allows for us to add numbers by not caring in which order we add them or how we group them before we add them. There are laws that relate multiplication with addition. Right? Another useful law. And it goes on like this. In this world of sets, we have similar fundamental laws that describe the behavior of the operations. For example, we have the law of associativity for union. And in fact, we can actually derive the law of associativity for addition from the union one, because we can represent addition in terms of union of sets. Then we have something similar to this with how multiplication behaves with the union. You see the similarity. We've got A intersected with B union C, A times B plus C. And then it expands to A times B plus A times C. So this expands to A intersected with B, union with A intersected with C. A with B, A with C. Now, when we learn these laws for numbers, we never were required to prove them. They kind of told us this is how it works, and we with our experience of arranging objects, we kind of felt, okay, this is maybe obvious that it should work like that. But the true reason why you didn't prove these things when you learned about these at school, maybe, is because you didn't have formalized the language in which you could carry out the proofs, right? And now for set theorem, we formalize the language, and we can have the luxury of proving such basic principles, and that's what we've been doing for the last 2 weeks. So let us now go to the operation of symmetric difference, and let's explore what are the fundamental laws it adheres to, and how can we prove them. First of all, let's write out the definition of symmetric difference. Well, this is a picture. This picture is actually a bit abstract, right? Because a set is not really a region. A set is a collection of objects. So if I want to make this picture a bit more precise, what I have to do with the notation that we've adopted for sets, I have to put dots in here. So these are sets in X and in Y. And then we pick that set, and that set is called the symmetric difference of X and Y. If I had done just this, then this would be called the ordinary difference. So then the symmetric difference can be seen as the union of doing that and the other one. So it's the union of X minus Y and Y minus X. The reason why it's called symmetric difference is because it makes this one into a symmetric operation, so that it doesn't matter in which way we put them. So X symmetric difference with Y will be equal to Y symmetric difference with X, and maybe that's the one we want to prove as a first result on symmetric difference. Just like with the absolute value of the subtraction of two numbers, the order in which you operate doesn't matter. Although with your ordinary subtraction it does, because then sometimes it gives you negative numbers, sometimes it's positive, depending on the order in which you operate. Okay, so let's start with trying to establish this, but I forgot now, we were supposed to first write out the formal definition. We kind of already did there, but let's write out a more explicit definition in terms of the elements. So this is the set of all those x's such that x is in x, or x is in y, and at the same time x is not in sorry, let me put it this way, and at the same time it's not true that x is in both x and y. So what I'm saying here is that when you've got an x and you want to figure out if it's in a symmetric difference or not, first of all it has to be in the union, so it has to be in one or the other, right? So it has to be in here, but then it cannot be in here. So this is another presentation where we present symmetric difference as x union y minus x intersection y. Okay? So this part says x is in either of them, and the second part says x is not in both of them. Great. So that's one way of defining it. Another way of defining it is what we wrote out there. So all the x's, so expanding now this equality, we could say it's all the x's such that x is in x and x is not in y, or x is in y and x is not in x. Now, if we look at these formulas as logical statements, right? This one and that one, they look quite different. But we can actually get one from the other by using the distributivity property of n and or over each other. A property similar to this rule, except not for sets, but for statements, mathematical statements, and here having conjunction and here having disjunction. So let's have a look at that. As a first step, let's try to establish these two things are the same. So, I want to prove x minus y union with y minus x is the same set as x union with y minus x intersected with y. Once I establish this, I'm going to know that the two definitions of symmetric difference coincide, and so then I can proceed with the study of the notion. Okay, well, establishing this equality intuitively is rather easy. We just draw the pictures and we see that they're the same picture. Maybe I should also elaborate on that. So if I try to do this carefully with pictures, this is what I would do. So the left hand side, right, I need to begin with two sets, okay, x and y, like this. And now, x minus y means taking this part, right? Y minus x means taking this part. And their union is just taking both together. On the other side, I will first compute x union y and x intersection y separately. So x union y is this. X intersection y is this. Right? And now I have to remove the intersection from the union. So I will then end up with the shade that is only vertically shaded, not the one that has crosses. And then I will end up with the same picture as that. Good. Now let's look at this more formally. And there are two ways to do that. One is to expand each of these as sets as we've done above. A bit quicker and more elegant way is to analyze what it means for a small x to be an element of the left-hand side. We then separately do a similar analysis for the right-hand side, and we want to come to the same conclusion. So let's analyze what it means for x to be an element of x minus y union with y minus x. So that's equivalent to, well, the outermost operation we have here is the union. So we now forget about what these mean. We abstract away a bit, right? We think of this as something union with something else, and so that we can say that this is the same as x being an element of the first something, or x being an element of the second something. Now we want to break down each of them, right? So what does it mean for x to be an element of that? It means for x to be an element of x, and x not to be an element of y, or x is an element of y, and x is not an element of x. And at this stage, I've come to an expression that has only element symbol and the logical symbols. This is how I know I stop. I can't break it down further. There's nothing to break down further. This is the most primitive, the lowest level relation we have, the element relation. Here, I could break it down further because I could break down x minus y further, right? But here we cannot break anything down further. By the way, please ask questions if you have questions along the way. So now let's look at the right-hand side. Let me actually do it on the right-hand side. So let's see what it means for x to be an element of this set. Okay? So once again, I abstract away a little bit. I think of it to myself as follows. X is an element of something minus something else. I don't care at this point what those somethings are. So that means that x is an element of the union, and at the same time it's not an element of the intersection. Do I stop here? No, because I have some things I can break down further, the union and the intersection. So being in the union means it's being in one or the other, or both, but that's included in the logical or. And then we have and it's important to put these brackets in, because we can't just move them around any way we like, because we have two different connectives, right? So that we don't misunderstand in our own statement, it's important to keep those brackets there. Now we want to say x is not an element of the intersection. How do we do that? Well, by abstraction. This means something is not true. So let's not care what that thing is yet. Let's just say something is not true. So it's not true that x is an element of x is intersected with y. Right? So an important step here. Otherwise, I can't break this down on its own. I have to separate it in terms of that and that. Great. So now we copy the left-hand side because the left-hand side cannot be broken down further. And here, we keep that negation, and then this is saying x is an element of x, and x is an element of y. And this is where we stop, because we've broken down all the set theoretic symbols. Everything is now expressed in terms of the element symbol. But we stopped here, we stopped there, but we didn't get the same thing. Okay, so we actually got to the point we started off there. I still wanted to clarify how do we get to that point. Now that we're here, we want to kind of relate these two things to each other, right? They kind of have the same ingredients, right? We've got the ingredients. That one is over here. We've got this ingredient here, right? We've got this ingredient. Do we have that ingredient? Not quite. Maybe I want to rewrite this in such a way we do. By bringing the logical negation inside. So this is not breaking down further. This is now applying logic. To match one of these expressions, to make a better match with the other expression. So and, now how does the negation go in? Let's abstract away and discover the principle of how we can bring in the negation for general mathematical statements. If I have not alpha or beta, right? This is saying it's not true that one of them is true. So that means to say that neither of them is true, right? So it is the same as to say not alpha and not beta. And here we can see the rule coming out, right? So the rule is when we bring in the negation, the or becomes the and. And now we can remember the rule and we don't have to redo this all the time. It's a beautiful rule and it's easy to remember therefore. Okay, so we've got here not x in x, but we can write that as this. And then we've got or, and we should keep this track of the brackets. Or that. And the bracket here is important. You see, I might have lost track of the bracket because now that I'm bringing this in, I might think, okay, what's the purpose of this bracket? No purpose anymore. So let's remove it. But no, because we've got and here and or here. So if I had removed it, I would get an expression that's no longer, that can be read, interpreted in different ways. And the other way of interpreting it would give me a wrong expression. So it's important that I'm working on this side, so rather keep the bracket. It's better to have extra bracket than to miss one, right? Great. So now we can say that the ingredients are similar. Well, the same actually. But still, the order in which they appear is different. So here, the positive statements are together and the negatives are together. Here, there's a mix of them. Maybe we can reshuffle it. How to reshuffle that? Imagine now going back and using our experience from numbers. If I had a plus b times c plus d. No, right. If I had a plus b times c plus d, I would have to multiply it out, right? But multiplying out works in two steps. When I have something like this, when I multiply it out, what I'm really doing is I'm first applying distributivity on one side, and then applying distributivity on the other side, right? Yeah? So let's use this experience and let's try to do the same thing here, where we're going to regard, in the first step, we're going to regard this whole thing as one thing. So again, we abstract away, and we come to an expression of the form alpha and beta, and that is being ORed with a gamma. So this is saying alpha and beta, both of them are surely true, or actually not surely true. Either both of them are surely true or the other one is true, right? So there are two cases when gamma is true and when it's not true. When gamma is true, then the whole thing is true, right? But when gamma isn't true, then both alpha and beta have to be true. So writing now this thing, can we see that this is the same as the other one? Let's see. So in here, both of these must be true, right? But again, now let's talk in terms of cases. So when gamma is true, both of them being true just means that gamma is true. If gamma isn't true, both of them being true means both alpha and beta are true. So in both cases, whether gamma is true or not, this gives the same result as this. Yeah? So this is how we can reason out that this is actually logically the same as that. Should I repeat this one more time? So, I'm claiming that this is equivalent to, this thing is equivalent to that. And I'm proving the equivalence in terms of cases for gamma. If gamma is, so there are two possibilities. Either gamma is true or it's false, right? If gamma is true, then this is true, right? And this is also true, right? So in the case when gamma is true, the two things are equivalent because both of them are true, and truth is equivalent to truth. Now let's consider the case when gamma is not true. When gamma is not true, for this to be true means for both alpha and beta to be true. But when gamma is not true, for this to be true means both alpha and beta to be true. Because when gamma isn't true, and still the conjunction is true, right? Now it means that is true and that is true. But remember, gamma isn't true. So, but then how can this be true if alpha is true? And the same for the other one. So in both cases we seem to get that the one is true if and only if the other is true, and this is how we can conclude that the two statements are equivalent. So equivalence for us means that one will be true if and only if the other one will be true. And if we're not happy with this kind of language argument, if we want something more visual, we can set up a truth table for each of them and see that they actually give the same truth table. Okay. So applying now this rule, I'm not going into more detail in this rule because this was actually needed to establish this kind of law, and also the other one with union and intersection. So we're already kind of supposed to be familiar with this equivalence. So I'm going to now keep one side and join that with this, and then conjunct it with joining this with the other one. And then I'm going to get x is in x, or, so let's keep my brackets, maybe here it's not necessary, but still, I'm going to keep it, or this, and x is not in y, or the other one. I actually didn't need these brackets, it's just that because I wrote these two things so close to each other, I felt like I should put brackets, but now I feel like I should remove them. Right, so what did I do? I treated this as one thing, as a gamma in here, and here is alpha and here is beta. And now I take this or that, and then AND it with this or that. So that's what we've got here. Okay. Is everyone fine so far? Can you see how I applied this pattern to go from here to there? Now in each of these now, I'm going to use the similar law with the OR and the AND swapped around. So I'm going to OR this with that, and then conjunct it with this ORing with that. So we're going to get x is in x, or x is in y, and x is in x, or x is not in x, and do the same thing here. X isn't in y, or x is in y, and x isn't in y, or x isn't in x. So at this point in the calculation, I'm just trying to be careful that I don't introduce a mistake, that I'm very carefully applying the logic rules to get to where I am trying to get. I also wasn't very careful with brackets anymore because the end inside here and the end inside here is now the same as this one. And with n we know that we can swap around brackets, so I dropped the brackets. Something weird happened now. We now have 4 terms, whereas here we needed 2 of them. So maybe that's bad news, right? But let's actually be more concrete now, and let's see what these terms are, and what are the extra terms in particular. So this term we see there. right? Good. This one, we don't see there, right? X is in X or X is not in X. What's that? Can we kind of erase that? In order for us to be able to erase that, what kind of thing should this be?
Always true.
Always true, right? Because we are doing conjunction with it, right? So if this is always true, the conjunction will give me the second one, so it's not going to affect the meaning. Is this always true? X is in X or X is not in X? It's always true, right? Well, at least in classical logic it's always true. And so we can remove this one, and also we can remove, for the same reason we can remove this one. X is not in Y or X is in Y. And then we end up with this, which I think should be very similar to the other one. It's almost the same. The order has swapped around on the second side, right? In there we've got the other way around, but we know that with OR we can do that, so it's no problem. If we kind of reflect on this as a whole, overall it is a bit complex, right? But each step was quite simple. Although there are few steps, so that's what makes it complex perhaps overall. Are there any questions on this? So what we've done now, we've established that being an element of this set, of the left-hand side, is equivalent to being an element of the right-hand side. And therefore the two sets are equal. Do you have any questions on this? Okay, so was it useful to anyone, or did I waste your time? Was it useful? Did you learn something new?
Yes.
Okay, great. Now that we have these sets are equal, we want to look at the basic properties of the symmetric difference. So now we can say, let's define these expressions to be X symmetric difference with Y. It turns out that symmetric difference has quite remarkable properties, and in fact, it turns out it behaves better than the absolute value of the usual difference of numbers. Am I right? I might be wrong, by the way. I think I'm wrong. I think this one is also quite nice. Let us actually make a table of properties for both of them to see how similar or how far apart they are from each other. So it's pity Brittany is not here today. I guess she was busy with many other things. Because now we're going to make explicit comparison between symmetric difference and absolute value of difference in numbers. So, X symmetric difference Y is equal to Y symmetric difference X. For numbers, we have absolute value of X minus Y equals absolute value of Y minus X. X symmetric difference with X equals empty set. For numbers, we have absolute value of X minus X is equal to 0. Let us draw pictures for this. For each of these equalities, we can carry out the proofs in very similar manner to the way we did it above, by analyzing what it means for something to be an element of the left-hand side, and then something to be an element of the right-hand side, and coming to the same logical conclusion. That conclusion being actually equivalent to each of the initial statements. So with the pictures, the left-hand side would be, so this is x and y, and now for the right-hand side, we've got this, right? And so that's the left-hand side and that's the right-hand side, and we can see that they must be the same. Okay, I want to take back what I just said. Not just now, but a few sentences ago. I said that we could use similar methods to arrive to these rules. Well, maybe yes, but maybe there is a better way. And namely, to use explicitly the definitions. For instance, for this one, if I expand symmetric difference in this manner, x minus y, union with y minus x. This was one of the definitions, right? Then I get quite immediately the equality. Because then it follows from the commutativity of union operation. We already know that union is commutative, so we don't have to go through that element chase argument. We could conclude it more algebraically using the already known properties of the operations. The same goes for this one. There is a similar reason for this, because now if we have x and x there, we will have, so your name is Brittany, right?
Yes.
Good. It means I didn't make a mistake, because I was talking a lot about you. So we're actually exploring the analogy between symmetric difference and the absolute value of the usual difference of numbers. So if we have x and x, then we will have x minus x, union x minus x, right? And x minus x is empty set, and empty set union empty set is empty. So that's how we can arrive to this. Okay? We don't really know what to put here, but we know some nice properties of this maybe, that we could try to see if the corresponding versions on the other side hold. Any suggestions? Do you know of any nice property of absolute value of the usual difference?
X minus 0.
Good. X minus 0 is x. And here we have symmetric difference of x and empty set is x. Okay. We actually have that, right? So that's can be easily confirmed. So this is all those things that are in both of them, but not in the intersection. Well, there's nothing in the intersection because it's the empty set. So it's all those things that are in both of them, and that's the same as x because the other one is the empty set. Okay? Anything more on this side? Okay, so here is one. A times, if we are talking about positive numbers, right? A times the absolute value of b minus c is the same as a times b minus a times c and the absolute value of that. Yes?
I just want to check the third one, is that not just the absolute value of x or not?
It's equal to the absolute value of x, yes.
Yes.
But we're now only working with positive numbers, non-negative numbers, and so we can write that. Yeah, that's a good remark, thank you. We have this, right? Can we adapt this here? Well, what do we use for multiplication? Any suggestions? What do you think will serve? Well, at least do we have any such law with multiplication here replaced with something? Maybe Cartesian product? Should we try that? So Cartesian product of x with y symmetric difference z, is it equal with Cartesian product of y symmetric difference with Cartesian product with z? I don't know. I don't think I've ever asked this question to myself. I don't think we have anything like this in the notes. So it's a new formula, if it's true, which was led to us from this analogy, right? So let's check. Let's analyze what it means for something to be an element of the left-hand side. We're working with Cartesian products on both sides, right? So we can safely assume that elements of left or the right, in both cases, will be ordered pairs. So let's take an ordered pair xy, or maybe AB. And let's analyze what it means for it to be in this set and separately there. So or pair will be this set if and only if A is in X and B is in Y symmetric difference Z, right? So that's if and only if A is in X and B is in, which presentation shall we use? Maybe we use this one. In Y, or B is in Z, and B is not in, and it's not true that B is in Y and Z at the same time. So we've broken down as much as we could go there, right? Now let's look at the right hand side. For this to be there, the brackets go this way. This is equivalent to AB being in X cross Y or in X cross Z, right? And at the same time, it not being in both. What do you think? Is it going to work out? You think it's going to work out? Okay, let's expand this further. This part means that A is in X and B is in Y. Put the brackets. Then we've got or A is in X and B is in Z. And not, this means A is in X and B is in Y, and A is in X and B is in Z, right? Okay. We've got something that's significantly longer. Let's look at the ingredients. So A is in X appears in both cases, but something bad is happening here, maybe not. Perhaps we can use the previous experience and know for now already that we will want to bring this in, because we'll maybe do the same thing there. Or maybe not. I don't know. What do you think is the best way to go? Yes?
Can't we say that because A is in X appears in both terms on the left, then we can say A is in X and it's in B is in Y or B is in Z.
I like your idea. Thank you. I like your idea. So we can bring out A is in X. So that's going to be A is in X and B is in Y or B is in Z, right? And not that thing we've got there.
Isn't there a problem with the not and then A is an M and then
Yeah, it might be. Let's see. This part seems to be the same as that part, right? This part is the same as that. So let's actually expand this and is this not as well. So if we bring this not inside, so let's bring it simultaneously twice inside. So once going inside, this is going to turn into OR, and the second time each of these is going to turn into ORs as well. We've got all the ends here, right? So we actually could have it written like this. and then all of them are going to become ors. So A is not in X, or B is not in Y, or A is not in X, or B is not in Z. Whereas here we have A is in X and B is in Y or B is in Z, and bringing the or inside we have, the not inside we have B is not in Y or B is not in Z, right? And now these ingredients are there, but this one isn't, right? Right? Something weird is happening. But remember, from the left-hand side, A must be in X. Right? Now, if A is in X, can A, at the same time, A not be in X? It can't, right? So does this mean we can erase this part? Does this mean that this thing is equivalent to A being in X and B being in Y or B being in Z and B not being in Y or B not being in Z? So let's see if they're equivalent in the two cases. So the two cases being now A is in X or not. Case 1, if A is in X, right, then A can't be, then this cannot be true, that A is not in X. So in the case when A is actually in X, the only way this OR statement is true is if it's true without these, which is the same as the second one. On the other hand, in the case when A is not in X, then both of these are false. So they're equivalent to each other irrespective of whether A is in X or not, right? So we can't move from here to there. But then, isn't this the same as that? It is, right? So, wow, actually it turns out that this equality holds. Shall we make a picture for that? Let's make a picture for that. Let's see how it looks like. If we made a mistake, the picture will show us the mistake, right? If you feel a bit not certain that what we did here was right, we could have actually broken it down further and went into factoring this out maybe with the end factor. I mean, doing the distributivity this way and then coming to the same conclusion. Okay, so how do we draw something like this? How do we draw Cartesian products, right? Well, Cartesian product can be drawn using Cartesian coordinate system. So let's shrink dimension down. Otherwise, we're going to get a 3D drawing. We can't do that on the flat surface. So Y and Z, let them be straight lines. So this is Y. Okay? So this set of all points on this segment. And so that's Y. And this one is Z. Okay? Now, X, let X be this segment. Okay? X Cartesian product with Y symmetric difference Z. Y symmetric difference Z is the one that I'm going to do with these dashes. This is Y symmetric difference with that Z, if you agree. Now we need to take Cartesian product of X with that. So all ordered pairs. This is this rectangle and that rectangle. Right? So that's Cartesian product of x with y symmetric difference with z. Does everyone see that? So what goes in the rectangle? Ordered pair via the coordinates. So if this is small x and that's small z, the ordered pair xz can be displayed as a point. And filling up displaying all the points like that will give us exactly the rectangle. On the other hand, if I do this, x Cartesian product with y and symmetric difference with x Cartesian product with z, what am I going to get? So now, copying the picture. So x Cartesian product with y will be this rectangle. And x Cartesian product with z will be this rectangle. And their symmetric difference is the same thing. So that's nice. The picture matches with what we got. I'm getting a little bit of a feeling that maybe it would have been easier to carry this proof out if we use the other definition of symmetric difference. Not the one we used here, but the other one. But you can check it in your own time if that is true or not. Okay, so we took a formula for numbers and we saw that an analogous formula holds for sets. Now, what about a very natural property that we pointed out for numbers right from the start? The associativity property. A symmetric difference, B symmetric difference, C being the same as AB symmetric difference than with C. A symmetric difference, okay, let me use X, Y, and Z. X symmetric difference Y, symmetric difference Z being the same as X symmetric difference Y symmetric difference Z. The corresponding property for numbers would say absolute value of X minus Y minus Z and absolute value of that is the same as absolute value of X minus Y minus Z. Is that true? This is the distance between X and Y. You measure the distance, and then you take the distance between that number and Z. It's a bit weird thing to do, right? So, would it be the same? I think you should be able to do absolute values better than I, because I haven't worked with absolute values.
3, 2, and 1, I don't think it works.
Oh, did you find a counterexample?
3 minus 2, absolute value of that is minus 1. Is not equal to 3 minus the absolute value of 2 minus 1.
Okay, that would be very interesting. So, this is 1, and that's, so the left hand side is 0. On here, on this side, we've got 1, and it's 2. Wow. So they're not equal. Right? Does this mean that the symmetric difference one will not be equal? Let's look at that. Let's first look at the picture. So if I want to compare symmetric difference of X and Y with the symmetric difference of Z, if I want to compare that with this, with pictures, I would do the following. I would draw three sets, X, Y, and Z. X, Y, and Z, and then I will start building the left-hand side set. So X symmetric difference with Y is this set. right? And now we want symmetric difference of that with Z. So remember how it works? We have to take the union, and the union would be this shape. So the inner part, so not that one, just this one, the Mickey Mouse part. And then we have to take away from the union the intersection, right? So where does Z intersect with the shaded area? Here, right? So if we take off the mask from the Mickey Mouse, what are we going to get? Well, shall we kind of do like this? So we're taking away this part, but everything else we are keeping, right? So we are keeping those two original parts, and then we are keeping also everything else in Z except those two parts. So we're keeping this, and we're keeping that as well. Okay? On this side, it would be, so what would it be on this side? So we've got X, we've got Y, we've got Z. First it's kind of the same Mickey Mouse, but now it's turned around, right? So first we're going to take this, the symmetric difference of Y and Z, and after that we're going to take symmetric difference of that with X. So that's taking this away and inserting all of these ones and these ones, right? So in both cases we get a nice picture. In both cases we get this, this, and this. That's what we get. So in both cases we get the same. According to the picture they must be the same.
Why is the middle part?
Because the middle part, on this side, the middle part was part of Z. That didn't fall in the overlap of Z and the symmetric difference of X and Y. So it's kind of alternating thing, right? So you take the union of all three, you take away all the intersections, but then you add the intersection of all three. So the formula actually becomes, and this formula can be generalized for longer expressions. So it becomes, take the union of all three, so take union of X, Y, Z. Then take away from it pairwise intersecting them. So take away from it what? The union of intersections, X intersected with Y, X intersected with Z, and Y intersected with Z. And then, so take away this union and then take union of it with all three intersected with each other. I don't think I wrote something useful now. It's actually longer than the other thing. But I just wanted to point out the pattern that, so those things fell out that were in the intersection of exactly two of them. But those that were in the intersection of all three of them were stayed. Okay, so wow. So something that wasn't true for numbers now is true for symmetric difference. And this kind of shows us that maybe symmetric difference of sets is actually a better version of the absolute value of the difference of two numbers. So let's try to prove this. And that's where we're going to conclude the lecture, at least as far as the video is concerned. We want to prove associativity for symmetric difference. It's not going to be, I don't think it will be easy task. I think it will be a long calculation. But hopefully not too long. What do you think? Which method do we use? Do we try to expand it in terms of the basic element level, or do we maybe expand it in terms of differences and unions. What is your suggestion? Do you have any suggestions? What would you do? I mean, if you had to do this computation now, what would you do? How would you move from here? Because remember, we have two definitions, right? So which definition would you use? Since in the previous proof we used the other one, let's use here the other one. So let's use this one. X is an element of X symmetric difference with Y. Minus Z union with Z minus X symmetric difference with Y. And so we get X is an element of X symmetric difference with Y, and X is not an element of Z, right? Or X is an element of Z and X is an element of X symmetric difference Y. Everyone fine so far? So now we break this further down. So being an element of the symmetric difference means applying the same definition. X is in X and X is not in Y, or X is in Y and X is not in X. So that alone is this part. And then we're taking that and X is not in Z. And then we're taking that, or X is in Z, and wow, this gets super long, right? X is not in X symmetric difference Y. So that's not being true that X is in X and X is not in Y, or X is in Y and X is not in X. Wow! This is even longer than I expected, huh? Can we handle this? I mean, psychologically. Is it at least broken down to pieces? There are lots of negations that can go in the expressions, right? Now I need to do the same thing for this, right? Okay, you know what? Let's be clever. This is the same as this, isn't it? Swap around. We know symmetric difference is symmetric, right? Commutative. This is the same as that, right? Okay, I want to match that. At least I want to keep Y there. So this is the same. I can also swap it around another time as Z symmetric difference Y, symmetric difference X. Do you agree? Now this formula works for any X, for any Y, and any Z, right? In particular, it will work for Z, Y, and X, right? So we're not going to repeat this calculation now. What we're going to do, we're going to switch around X's and Z's in this expression and get the answer like that. So that's being a bit clever. This is good. We are simplifying life a little bit. Perhaps this gives us more courage now to break this down further, up to the point where we will see that switching around X's and Z's is going to give the same answer. That's what we want, right? So we have this. The other one will be exactly the same thing, but X's and Z's switched around. And we would want to show that that logically is the same as the switched around version. So if we simplify this to the point where the entire expression is symmetric in terms of switching around x's and z's, then we're done. So let's continue the calculation. We are now trying to aim to put this in a form where the way x's appear is the same as the way z's appear. Okay, so where do we start? You can see better because you're further away and you can see the bigger picture. And like focusing on each little bit, I can't see the big picture. Okay. What is happening here? Wow. Wow. How do we, what do we do? I mean,
Suggestion.
yes,
You could, the x is an element of z,
right?
sorry, x is not an element of z, it's in the first large group of brackets.
Yes,
You can try to move that into both of the orbs.
into this. Oh, so they're together.
So
That's actually
it's,
a good idea, yeah.
Three adds, three...
Good. I like your suggestion. I'm going to do that. So I'm going to use this distributivity here with and or. So I'm going to move this inside the or. So then I'm going to have this and x is not in y, and x is not in z, or x is in y, and x is not in x, and x is not in z. So that's this part up to this point. Should we try to do something similar on the other side by first bringing in the negation? So then that's or. So let's actually first bring in the negation. So we've got x is in z, and now we want to bring this in. And we're going to do it twice, right? So this is going to swap around and that's going to swap around. So we're going to have x not in x, or x in y, and x not in y, or x in x. Yeah, do you see what I did? Okay? But now I have n and also n there. So I can remove this bracket. Right? Okay? Now we need another suggestion.
Show me the last bit is false.
What is false?
Well, it says x is not an element of x, or
I noticed that this or, we've got ors here. Right? We can remove this bracket. So we have ands, so we have or, we have two and expressions, ors, right? And now maybe we can do something similar here, have ors of and expressions or something like that. But wait a second, here we have ands of or expressions. So maybe we want to swap it around to make it similar to the first one. So overall it will be or of the and expressions. That's one possibility. Otherwise, we could do the other way around, that take some of these things out from there and then have it in the end form. I'm going to copy down the first line. And then try to group it like this. Or should we do it first here? Let's actually first do it here. Shall we? Let's be clever again. We know that when one operation distributes over the other, we can multiply things out. In the sense that here we can have this and this, or this and this, or and so on. Like with A times B, A plus B times C plus D, overall gives all possible products, right? A times C plus B times C plus A times D plus B times D. And that's only because of distributive law for multiplication over addition. And we have that law for join and conjunction, disjunction, so we could use the same shortcut. And then we would have x in z, and now I'm going to multiply them out. So this and with that and so on. So we're going to have x not in x and x not in y, or x not in x and x in x. That's false, right? And we are ORing with it, so we can just disregard it. We don't have to keep it. So this goes away. Then we have that x in y and x not in y. Well, that also goes away. So you see that actually was a good idea. And then we have x in y and x in x. We are now getting this also in the form of OR of end expressions. We have to just bring this in there and bring it in there. Wait, are we? No, we are. Yes, we are. So again, copying down the first line. And then here we have this ended with that, or that ended with the other one. But now it's going to be OR, so there's an OR here, so I don't have to keep the brackets there anymore. Here.
I know the one you just read, which is the repeating of the first line.
It's supposed to be. Thank you. Yes. Oh, thank you very much. You saved our lives, because otherwise we would have, our ship would have sunk, right? Would have hit the rock. So x is in z, and x is not in x, and x is not in y. Or x is in z, and x is in y, and x is in x. Right? This is what we get. Now, magic. Take this expression and swap around x and z, capital X and capital Z. Are we going to get an equivalent expression? If I swap these around here, if I want it to be equivalent, for this part I need to find another one that has x not in, so y still not in y, but x in, not in x and x in z, right? Do we have such a thing? So x not in y. There we go. Right? This pairs up. These two pair up. And here, this is symmetric. By swapping around x and z, we don't change the meaning. And also this one is symmetric. We're done. Right? So, now we can do this, right? So we can now say that x being an element of x symmetric difference with y symmetric difference z is equivalent to, we agreed that whatever calculation we would get here, because we can match this expression to that form, we can swap around x and z and get a calculation for the other side. So now, doing that, we will get x in z, and x not in y, and x not in x, or x in y, and x not in z, and x not in x, or x in x, and x not in z, and x not in y, or x in x, and x in y, and x in z. So that's what the right-hand side is equivalent to. But now, we've got a disjunction of things in both cases, and you see this part is the same as that part up to rearrangement of terms. And this part is the same as that one. These two are the same up to rearrangement of terms. And this one is the same as that one up to rearrangement of terms. And the other one is the same as the other one there. So then they're equivalent. Okay, so apart from the fact that we kind of reached the goal, and by the way, in mathematics, when you reach the goal, that's not when things finish, that's when things start. So then you start reflecting on what you did and making all the discoveries out of it. So we've reached the goal, but now what are the lessons we learned here? Wow, how much easier it was to establish this with pictures, right? Now that shows you how useful pictures can be in mathematics. With pictures, you can come up with an idea that with symbols, with symbols, if we were not sure this would have worked, we would have probably lost courage and said, okay, probably it's not going to work, right? But we knew it should work with pictures. So the pictures allow us to kind of predict much further ahead and be more confident in our calculations. So that's one thing. Another thing is symmetry. Symmetry plays a crucial role in mathematics. It was thanks to symmetry that we could have cut short our calculations in half, right? We used symmetry here of x and z to see that whatever calculations we do here, the same calculations can be done there. And symmetry is also kind of geometric phenomenon, right? And so this shows us how useful things like pictures and symmetry can be for mathematical calculation. Okay, well, there is one more property of symmetric difference, associativity. There are more. It has many other beautiful properties. And some of them are in the lecture notes. One thing is clear, symmetric difference is a bit better than the absolute value of the difference of numbers because of the associativity law. And I think this is the point where we can conclude this lecture. Any questions? Okay, thank you.